In this video, we're going to learn how to convert energy from electron volts to joules. Specifically, converting energy from atomic or nuclear scales to the human or macro scales. Along the way, we are going to look at the units on two different scales, what that even means and what other examples are. We're going to look at the conversion factor itself, and then we're going to look at a worked example. So on two different scales, really what we're talking about is on the macro or the human scale versus on the atomic or nuclear scale. And we have three quantities we're going to look at. One of those is mass, the variable m. On the macro or the human scale, we've got the kilogram, and those are examples of things like a car or a person. We determine the mass in kilograms. At the nuclear atomic scale, we have what's called the universal mass unit, or U. In outdated sources, you may still find reference to atomic mass unit, or AMU. That's a couple decades out of current usage, but they are the same size and they mean the same thing, U and AMU. Examples of those things might be the proton, the electron, or quark. The next quantity we can look at is the electrical charge, Q. On the large scale, human scale, and so forth, is the coulomb. And that would be a measure of the charge on a steel rod or an aluminum sphere. But at the atomic or nuclear scale, we talk about charge being measured in elementary charge units, or little e. And that would be the charge on an electron, a proton, or an ion, a quark, or a lepton. So very, very small scales. And of course, the charge on the large scale, the human scale, is built up off many, many, many of these elementary charges. So this would be a very large number of these small charges. Lastly, the third type of energy, third quantity is energy. We're probably all familiar with joules, which occurs at a human scale. These are things like potential energy of a book or the energy released in a batch of a chemical reaction. On the atomic or nuclear scale, the unit of energy is the electron volt, or EV. The origins and meaning of that name are not important for our usage of it here. There's a nice history and physics behind where that comes from in the field to look into that. If you're curious about learning more, would be in the field of physics. So examples of things measured in electron volts might be the electromagnetic energy of a photon. It might be the kinetic energy of a moving particle that is extremely tiny, like a neutron or a proton or some other kind of very, very small atomic or nuclear particle. So what about the conversion factor? Well, basically we have a small unit, the electron volt, which is very, very small. And we have a large unit, the joule. And that large unit, the joule, if we have one very, very small charge, we would expect much fewer of them, much fewer of the large ones. Many, many fewer joules than electron volts. Electron volts are really tiny compared to a joule, so if we have one of them, we'd expect a very tiny number, 10 to the minus 19 joules. Another way to express this would be to consider looking at the large. The large unit being the joule. The large unit being the joule compared to an electron volt. So we have our large unit, and we have one large unit, and so we would expect a very large number of small units. In fact, 10 to the 19th is what we see. 10 to the 19th of these little tiny things in one joule. Now, those are an expedient way to write them out, but when we're doing the science, we want to use unit analysis frequently. And for the calculations we like to do, it's best to express them as a ratio. And the meaning of those ratios, if we were to consider this one, we have 1 electron volt is a very tiny number of joules. But this electron volt is the same size as this many joules, so that means the ratio is 1, and we call that unity. And all conversion factors are like this. We have 1 of one unit and a different number of the other unit, but since they are the same size, the ratio of them is 1, and that aids us in our unit analysis. Similarly, we can look at this one. And we see 1 joule, the big unit. Well, we'd expect a very large number of the small ones. And sure enough, we have a very large number of the small ones. And this next one is just the last one flipped. And so it is also still equal to 1. So there are a number of ways that we can express this unity, this conversion factor. The one we are going to use is this last one that I've identified in red. It is a very tiny number of joules per 1 electron volt. And we're going to use that one because it has particular advantages to us, and this number that we have in the numerator here is one that we can use for other things in chemistry and physics. So we'll use that one number. And what we should do is store that in our calculators as the letter Q. And as a reminder how to do that, we type in the number 1.602 176 634. And we're going to enter it using calculator scientific notation. So that is second, comma, negative 19. We never ever write a number in scientific notation as times 10 caret. You may have been taught that, you may have been shown that, but it will almost always give you the wrong answers when you're doing scientific calculations. It's a special feature programmed into graphing calculators by scientists for scientists so that it can do the mathematics on scientific notation properly. So never use times 10 caret. So we now have this number in scientific notation. We're going to store it by using the STO key, and we're going to store it as the letter Q, which is alpha 9, because the Q is in the letter green, we'll have the green key, and we hit enter. Now if we clear our screen and we hit alpha 9, it draws up the letter Q and recalls the number. So now we never have to enter that number again. So now we've stored that conversion factor, and now let's get to our worked example. So we have an electron absorbing a photon of 1.89 eV. And we want to know how much energy that is in joules. So we're going to start out with our unit analysis. We're given a certain number of EV, but our answer needs to be in joules. So we need to multiply by a factor that the units will cancel, and we'll end up with joules. So you can clearly see what we want is joules per EV, because then the EVs will cancel, because EV divided by EV is 1, and so we'll have joules equal to joules. So that guides us in the math that we're going to do. Well, we have 1.89 electron volts, and we have our conversion factor Q, which is this joules per EV. That's our conversion factor. This is this that we stored as EV. So if we were writing this out, we would see the 1.89 EV, we see our conversion factor, and then we end up with an answer in joules. So the way we would type that into our calculator is we would hit 1.89 times alpha 9, which is that Q number, and lo and behold, we get 3.028 times 10 to the minus 19th. So that's this number that we have right here. And then lastly, we need to express it with a proper number of significant digits. We look at this 1.89, which has 3 significant digits. Our conversion factor has 10, so therefore our final answer can only have 3 significant digits. This 8 makes this closer to 3.03 than 3.02, so it rounds to 3.03, and therefore this is the number of joules in 1.89 electron volts. And if we step back and ask ourselves, does this number make sense? Well, if we had 1 EV, then we had 1.6 times 10 to the minus 19th joules. So 1.89 EV is about 2 electron volts, so it should be about 2 times this number. So it should be about 3 times 10 to the minus 19th. Conceptually, we can say we only have about 1 of these very, very tiny things, so we're going to have an extremely small number of the big things. So just a number of ways to think about it when we do our unit analysis and conversion.